In the previous episode, we talked about how to multiply a matrix by another matrix. And in an episode before that, we noticed that column vectors can be understood as just special matrices that only have a single column. So today we're going to be focusing on multiplying a matrix and a vector. And we're going to study the effect on that vector of multiplying by different kinds of matrices. So to start with, let's observe that if our matrix A has n columns and a vector x has n entries, then it is possible to multiply that vector by the matrix A on the left. So if I want to do A left multiply x, then this is possible as long as the matrix and the vector are compatibly sized. So if A is m by n and x is n by 1, then these objects are compatibly sized for this kind of matrix multiplication. So as a warm-up, let's do a quick example. Let's suppose that I have a 2 by 2 matrix A. 2 by 2 consisting of entries like 4, 1, 2, 5. And let's suppose that I have a vector x consisting of the column 3, comma, minus 1. Let's go ahead and left multiply this matrix to this vector. So let's calculate A times x. So once again, dot products are what we're going to be using here. Taking first of all the dot product of the first row with this column, we get 4 times 3, 1 times minus 1. So that's going to give us a result of 11. And then we're going to move to the next row of A. So we have 2 times 3, 5 times minus 1, and that's going to give us a result of 1 from 6 minus 5. So observe that when we multiply a matrix to a column vector, the result that we've gotten is another column vector. And this makes sense using the properties and the principles that we established in the previous episode. When the matrix A has m rows and n columns, and the vector x has n rows and 1 column, then when we multiply these together, these inner dimensions basically cancel out, and we're left with something that has m rows and 1 column. Because matrix multiplication turns a column vector into another different column vector, we often will think about matrix multiplication as transforming one vector into another, or changing one vector into another. So in this episode, we're going to explore the transformation that is induced by matrix multiplication by various matrices A. So let's start, for example, by exploring the effect of multiplying a vector by this matrix here, the 2 by 2 matrix 4, 0, 0, 4, that has 4s on the diagonal. So let's just play around for a minute and explore and experiment. Suppose that I start with the vector x is equal to something like 1 comma 2. I'm starting notably with a vector that has 2 entries so that I can multiply it by this 2 by 2 matrix. So if I apply the matrix A to this vector that I've chosen for my experimentation, Let's calculate the result. If I take the dot product of this top row with my column vector, I get 4 times 1 plus 0 times 2, result 4. And I get, from the second row applied to that column vector, 0 times 1 and 4 times 2, which is result 8. Let's do another experiment with a different vector. Let's, for example, define a vector x equals -3, 0. And let's go ahead and apply that matrix A, 4, 0, 0, 4, to that vector, -3, 0. So this row, dot product with the vector, gives us a result of -12, and this row, dot product with this vector, gives us a result of 0. So something I notice, as I apply this matrix A, we see the vector 1, 2 getting transformed into the vector 4, 8. As I apply this matrix A, we see the vector 3, 0 getting transformed into the vector -12, 0. So I'm asking myself, how would I describe the transformation that has occurred? How would I describe the transformations that turn these initial x's into the results of this matrix product? Well, it looks to me like what has happened in both of these experimental cases is that the initial vector has turned into something that is 4 times longer than it was before. Based on the results of my experiment, what I would describe in terms of the effect of multiplying by this matrix A is that A has the effect of transforming vectors by scaling them by a factor of 4 and making them 4 times larger than what they were before. Let's do another experiment with a different matrix. Let's go ahead and apply this matrix A to a couple of different vectors and see if we can understand or describe the effect of this matrix on vectors. So let's go ahead and do some experiments. Starting, for example, with a vector like, once again, 1, 2. Let's go ahead and apply the matrix to this vector. So 0, 1, 1, 0 being applied to the matrix 1, 2, this column vector. If I calculate the result using these dot products, then I have 0, 1 dotted with 1, 2, and then I have 1, 0 dotted with 1, 2. So the result of that matrix multiplication is 2, 1. It has taken the vector 1, 2, and it has turned it into the vector 2, 1. Let's do another vector for another experiment. Once again, I'll get my vector -3, 0 out. That's a nice one. And I'll go ahead and apply my matrix to this new vector to see what happens. So that first dot product 0, 1 dotted with -3, 0 returns 0 in that first entry. And then the second dot product returns -3. So as a result of applying this matrix A to my experimental vector x, I have gotten the result 0, -3 from that. So now I'm going to check see if I have enough data to articulate what is happening here. My matrix has turned the vector 1, 2 into the vector 2, 1. My matrix has turned the vector -3, 0 into the vector 0, -3. So one of the things that I'm noticing is that it's taking the entries in the vector x and it's swapping them, right? Like 2 and 1 are switching positions and -3 and 0 are swapping positions. So one way that I could articulate the effect of A on vectors is that it swaps the first entry and second entry. We can also understand the effect of A graphically. Let me go ahead and draw for us a little xy plane here. And let me start by drawing our initial experimental vectors x. So here's our first experimental vector, x equals 1 comma 2. So the initial experimental vector 1 comma 2 would be drawn like this. I'll call this x1 for the first experimental vector. Now, when we applied the matrix A, what we got as a result was the vector 2 comma 1. So the result of that calculation is over here, 2 units in the x direction and 1 unit in the y direction. So here is the first experimental vector after the matrix A has been applied. Our second experimental vector was this guy, -3, 0. So the second experimental vector would be located -3 units along the x-axis. I'll call it x2 for the second experimental vector. And then after applying the matrix A, we got the result 0, -3 along the negative y-axis. So graphically, if I'm going to articulate what has happened to these vectors after the matrix A has been applied, is there seems to be a reflection going on, a reflection across a diagonal line in the xy plane. It looks like the action of A is to flip a vector across this diagonal line and reflect it over the line y equals x. So that would be an alternative way to describe the action or the effect of this matrix on vectors, which is that it reflects vectors across the line y equals x in the xy plane. Let's explore the effect of matrix multiplication by another guy here, A equals cosine 45 degrees, sine of 45 degrees negative, and then in the second row, sine of 45 degrees positive, cosine of 45 degrees positive. Now, using the unit circle, you could also express this guy in the form 1 over root 2, negative 1 over root 2, and then moving to the next row, 1 over root 2, positive 1 over root 2. This would be equivalent to the matrix A that we were given in terms of these trig functions. So once again, let's set down a couple of vectors for an experiment. Let me just start with some really simple vectors to try and make the calculation easier because already this matrix A is relatively complicated in terms of the values it contains. So let me start with the first experimental vector, just 1, 0. And let's see what happens when I apply the matrix A to that result. So if I apply the matrix A, actually I'll just copy paste it because it's a lot of writing to do. I apply the matrix A to this vector. Then if I take the dot product of the first row of A with this column vector, I will get in the end just 1 over root 2 because that times 1 is equal to itself. So let me put down here 1 over root 2. And similarly, the dot product of the second row with this matrix is again 1 over root 2. Let's throw down another experimental vector here, another simple one, just to make the calculation straightforward. Let's try, for example, 0, 1, and let's apply the matrix A to that. I'm going to copy paste a lot from before. So if I apply this matrix to the second experimental vector, 0, 1, then the result of the first dot product is going to be negative 1 over root 2, and the result of the second dot product is going to be positive 1 over root 2. And then just one more experimental vector to help me see what's going on, because it may not necessarily be clear yet. Let's do another really simple experimental vector, this time pointing in the negative x direction. I'm going to steal this. If this time I'm multiplying the matrix A to the vector negative 1, 0, the result of those dot products is going to be negative 1 over root 2 and negative 1 over root 2 again. So let's go ahead and graph these experimental vectors and the results, what we got after applying the matrix A to these vectors. Here's the vector x1, which started out pointing just 1 unit in the positive x direction. Here's the vector x2, which started out pointing 1 unit in the positive y direction. And here's the experimental vector x3, which started out pointing 1 unit in the negative x direction. Now, when we applied the matrix A to our first experimental vector, the result we got approximately 0.7, 0.7 for the purposes of helping me graph. So that would be, roughly speaking, around here. This would be the result AX1 after the matrix has been applied. If I'm going to graph the result of applying A to my second experimental vector x2, in this case, the result of that matrix multiplication gave us a negative x component and a positive y component. So that would be pointing over into quadrant number 2, like this. And then finally, when we applied our matrix A to the third experimental vector, the result of that had both a negative x and a negative y component. So in this case, the result of applying matrix A is down here in quadrant number 3. So let's have a look at this. The matrix A is turning x1 into ax1 here. The matrix A is turning x2 into ax2 in quadrant 2. The matrix A is turning x3 into ax3 down here in quadrant 3. So how would you articulate what A is doing to these vectors? What is the effect and the transformation being caused by matrix multiplication in this case? For me, it looks like what's happening is rotation. A is taking each of these vectors and is rotating them counterclockwise. Specifically, it looks like the vectors are being rotated counterclockwise through an angle of 45 degrees. The exact same 45 degrees that has appeared in the initial formula for our matrix A, cosine and sine of 45. So that's pretty significant. We will see in a couple of episodes how this particular matrix gives rise to a 45-degree rotation. Here we've just seen it experimentally though. So I would summarize our results by saying that the effect of this matrix A is to rotate counterclockwise through an angle of 45 degrees. And that's how this particular matrix works to change or transform vectors. Finally, let's go ahead and explore this last matrix here. A is equal to 1, 0, 0, 1. So ones on the diagonal and zeros elsewhere. Once again, let's just throw down some experimental vectors and apply A to them and see what happens. If I take, for example, the vector x, which is 3 comma minus 2, and if I apply the matrix A to that, then the result of those dot products is going to be in the top row 3, and it's going to be in the bottom row minus 2. Let's do this to one more vector just to confirm our initial findings. If I throw down an experimental vector whose entries are 4 and 5, and I apply a matrix A to that, then the dot products resulting from this matrix product would give us values of 4 in the top row and 5 in the bottom row. So, what do we observe about the quote-unquote effect of this matrix A on our experimental vectors, which took 3 minus 2 and turned it into 3 minus 2, and took 5, 4 and turned it into 5, 4? Well, the effect as I would articulate it is that A did not do anything to these vectors. In the end, the vectors are exactly the same as how they started. So this particular matrix here, this matrix with ones on the diagonal and zeros elsewhere, is a very special matrix, which is called the identity matrix. So for example, in 2 dimensions, it's 1, 0, 0, 1. In 3 dimensions, it's 1, 0, 0, 0, 1, 0, 0, 0, 1. And in 4 dimensions, 5 dimensions, 6 dimensions, it follows this same general pattern. If you want to talk about the identity matrix, it has a special symbol. We denote it using the symbol I for identity. Or if you want to be specific about the size of the identity matrix, you might also see it called I with a subscript of n to just communicate that it's the identity matrix specifically that has n rows and n columns. But in general, if you see the symbol capital I describing a matrix, that is talking to you about the identity matrix. And this matrix is special because when you apply it to vectors, it does absolutely nothing at all. If you take the identity matrix and apply it to a vector x, the result is still equal to the vector x. That has not changed. Even further than that, if you take this identity matrix and multiply it by some other matrix, for example, if you do I times B, the result of this is just going to be the matrix B unchanged, assuming that I and B are compatibly sized. It also works in the other direction. If you have a matrix A and you multiply it by the identity on the right, you will get back the matrix A, assuming that the identity matrix is the right size for this product. So the identity matrix here is basically the matrix equivalent of the number 1 in scalar multiplication. Like if you have the number 1 times any other number, like 4, the result of that is 4. If you have a number 5 times 1, the result of that is 5. So I is the matrix equivalent of the number 1. Okay, so that concludes today's episode. Today we focused on multiplying matrices with vectors. And matrix multiplication takes a vector and turns it into some other vector. So matrix multiplication can be understood as a way of transforming one vector into another. Now, some special matrices have very clear, straightforward effects on vectors. For example, our matrix here with 4s on the diagonal had the effect of scaling vectors by a factor of 4 and making them 4 times longer than they were originally. This matrix here with 0s on the diagonal and 1s on the off diagonal had the effect of reflecting vectors over this diagonal line. And this matrix here with cosines and sines of 45 degrees had the effect of rotating vectors through an angle of 45 degrees. So different matrices can have different effects on vectors, and some matrices have very special effects on vectors.